The human pose analysis in videos has many applications such as sports analysis, healthcare, CG animation, and so on. To analyze human poses, humans manually annotate correct key point locations in each video. However, when the query video is capturing multiple people, manually annotating every video is impractical. To reduce such annotation cost, human pose estimation has been studied. In typical approach, heat maps are output for each key point, and these are integrated to estimated pose. By human pose estimation, we can automatically obtain human poses in videos. However, it often performs poorly on test phase due to a domain gap between the train and the test set. Then, how can we efficiently get accurate human poses in unknown videos? To address this problem, we video-specifically train a human pose estimator with few manually annotated poses. Based on this solution, our research question is, how can we train the human pose estimator with minimum annotation cost? For this research question, we employ active learning and transfer learning. By selecting informative samples, we efficiently improve the performance on the test video. Also, by fine-tuning the pre-trained estimator on a per-video basis, we overcome the domain gap. In this study, we introduced video-specific active transfer learning. This is the overview of our approach. Given an N-label query video, we actively select the samples to annotate. Then, we retrain the human pose estimator. This cycle is repeated until the stopping criterion is met. Now, our focus is on following questions: how to select the samples, how to retrain the estimator, and how to stop the ATL cycle. Selection criteria in active learning can be categorized into uncertainty-based and diversity-based. Uncertainty-based criteria can detect misestimated samples, but it tends to select biased samples in batch, called for selection bias. On the other hand, while diversity-based criteria can select representative samples, it may select easy and informative samples. Multi-peak entropy quantifies uncertainty in human pose estimation using local peaks in heat map. Temporal pose continuity utilizes the temporal change of key point locations. However, these methods are discarding heat map information and designed only for key point level uncertainty. In comparison, we propose temporal heat map continuity to make full use of these temporal heat maps. Our THC measures uncertainty by calculating the distribution distance between the temporally adjacent heat maps. In this study, we use the sum of absolute difference as this distribution distance. This allows us to quantify the uncertainty from the rich temporal heat maps and its change. Furthermore, while existing methods are considering key point level uncertainty only, we introduce whole body pose naturalness, which quantifies pose level uncertainty. The idea of double view is based on anomaly detection of the human poses. To this end, we train the autoencoder with the natural pose labels in the dataset. Then, it becomes able to reconstruct natural poses. Here, when the estimated poses are input into this autoencoder, it cannot reconstruct any natural human poses. Therefore, the reconstruction error becomes large for unnatural poses, so we can use this pose level anomaly score as uncertainty. Next, we propose a method to avoid selection bias and easy sample selection by combination of uncertainty and diversity. So, how can we combine uncertainty and diversity for efficient learning? In our dynamic uncertainty weighting, we modify the acquisition function of coset as shown here. When selecting every new sample to annotate, we combine its diversity score in coset with uncertainty. Based on the estimated performance, we dynamically balance the weights between uncertainty and diversity. In terms of retraining in ETL, Cho et al. Proposed active continual fine-tuning. In this approach, a pre-trained CNN is continually retrained with annotated labeled samples. ACFT reduces samples to retrain by limiting them to misclassified samples. However, this is designed for classification tasks and cannot be applied to human post-estimation. On the other hand, we adapted the definition of retraining samples so that it is usable for human post-estimation. In retraining phase, we reduce redundant samples following this equation. To determine the appropriate timing to terminate active learning, mean error was proposed. It stops active learning when the average error on label samples exceeds the desired accuracy. However, it cannot guarantee desired accuracy in our setting and leads premature stop. To address this issue, we introduce our novel stopping criterion, SCOLD. By guaranteeing desired accuracy on all label samples, SCOLD can accurately terminate active transfer learning along with specified performance. Our contribution is the proposal of active selection criteria suitable for human post-estimation. Furthermore, we adapted the ACFT-based retraining in our video-specific ATL. Finally, we proposed a novel stopping criterion to realize accurate termination of ATL. For experiments, we use PostTrack 21 and JLDB POS measure large-scale datasets for human post-estimation. For the metric, we used area under the learning curve, which corresponds to the efficiency of ATL. Here are the results of the video-specific ATL. Our method consistently outperforms the comparative methods. The ALC values for both datasets are shown in this table. Our method achieves state-of-the-art learning efficiency towards existing methods. The AP values for the labeling ratios of 5% and 20% and ALC values are shown in this table. This table is demonstrating that each component of our method contributes to performance improvement. Here, we validated our uncertainty criteria with others by observing uncertainty transition. We can see that our criterion decreases uncertainty as estimation performance improves, while some comparative methods cannot reflect the performance in uncertainty measurement. This is the estimated result for the video shown at the beginning. Although only 10% poses in the test video are annotated, ours can achieve significant performance improvement from the initial inference result. Finally, this is the comparison of stopping criterion. For each threshold for AP, our score can avoid premature stop and terminate ATL more accurately. This is the conclusion. Thank you for listening.